So thank you for the introduction. I'm Federico Bassi, and I'm here to present our work that deals with the experimental and simulated displacement in cracked specimen of p91 steel operating in creep conditions. The motivation for this work comes from the live prediction of crack components that operates in creep conditions. And nowadays, this successful parameter, cracking parameter, is the C star that correlates the crack propagation rate, and it can be determined experimentally by CCG tests and by analyzing the crack propagation rate and the load-like displacement rate, and also numerically by finite element analysis. This work presents the results of CCG experimental tests that were performed on p91, and then propose a model, finite element model, that numerically predicts the CCG behavior by analyzing, firstly, the characterization of the uniaxial creep properties of the material, and then, in order to achieve the crack propagation, a damage evolution model based on the ductility exhaustion was also used. The material is a modified p91 used in power generation industry, and the operating temperature is 600 centigrade degree. The elastic and plastic properties that you see in the table have been extracted from high temperature tensile tests. And also, our research partner Tenaris provided a uniaxial creep test. Here you can see the Norton law that shows the minimum creep strain rate associated to the test stress. But for what we know, if we want to represent, if we want to have a very good estimation of creep crack properties, we should not rely just on a law that takes into account the secondary creep. So we just analyze different uniaxial creep models. Among them, we have like some time-dependent models. The one by Kashanov, Liu, and Murakami. They both are explicitly dependent on time. And there are basically a couple of constitutive equations that define the creep strain rate and the omega and the damage rate. And they have good, they can be applied to the multi-axial case, both by the sigma r. And then another strain-dependent one strain-dependent model by Graham and Walls, in which time dependency is implicit in the creep strain. And for this reason, it gives less problems in the numerical applications of this model because of the numerical time integration of finite element simulations. So we have used this model, which is basically a combination of 3 power laws, and we have determined the 9 material constants for our material by fitting the experimental data that covers a range from 90 megapascal till 160. And we have validated our model by using a 3D axisymmetric simulation. For this purpose, we have to find a creep subroutine. And these are the results. We can see both the experimental data as markers and then the lines as the results of the model. As we can see, we have a good estimation of the creep behavior for the material, maybe not so good at one case, so 130 megapascal, where we have slightly overestimated the time to failure of the specimen. And let's continue with our purpose, which is the determination of the CCG resistance for the material. For this purpose, we have performed CCG tests on p91, and obviously, we have acquired during this test load line displacement and the crack propagation in order to be able to estimate C star parameter experimentally. And we have studied 3 initial stress intensity factor conditions covering 15, 19, and 21 MPa square root of meters. These are the results in form of crack propagation as a function of time, normalized time, and also in terms of load line displacement. These results were used to obtain the C star parameter, and according to the formula that you can see. And as in the previous presentation, even if we have accounted for the transition time and the initiation criteria, so at crack propagation of 0.2 millimeters, we still have, at very low stress intensity factors, a point where the relationship between C star and crack propagation rate is not unique. Let's move on the numerical models that we have used in these papers. We have studied both two conditions to the model with linear plane strain elements, and then a 3D model with the A-node brick elements with reduced integration. At the crack tip for both simulations, a mesh with an average mesh size of 100 microns was used, and this is by the order of magnitude of the grain size of the material. Crack propagation was reached thanks to the Creek exhaustion approach, as I already said, and that defines the damage omega as a ratio between the equivalent creep strain and the multi-axial creep ductility epsilon f star. How to express epsilon f star? We have used a model by Wen, which is a modification by a Cox and Ashby model based on the cavity growth model, and that expressed the multi-axial creep ductility as a function of the uni-axial creep ductility, the creep strain, creep exponent n of the Norton law, and the stress triaxiality that was achieved by the numerical simulation. Crack propagation was obtained with two different methods. On the 2D simulations, we have used a multi-point constraint that releases nodes as soon as the omega of 0.99 is reached. And in the 3D simulations, we have determined another user subroutine, user-defined field variable, that when omega reaches 0.99, slightly reduces the elastic modulus to a unit value, causing the crack to propagate. In the previous uniaxial creep curves, we have seen that there is very large range of uniaxial creep ductility, ranging from 0.04 to 0.36. For this reason, study different values of uniaxial creep ductilities in a sensitivity analysis that you will see in the next slides. These are the results of the numerical simulation, 2D and 3D, and the comparison with the experimental data. In the first, this graph, you can see the crack propagation as a function of time, and then in the second graph, there is the load line displacement as a function of the normalized time. Here you can see also a video, if it works, that shows the damage evolution during the entry simulation at the initial stress intensity factor of 15. And as we can see, we have a good representation of the crack front compared to the experimental one, and we can also see the damage progression at the sides, in the side grooves area of the specimen. So we have obtained a good estimation of the crack propagation rate as a function of time in all the three experimental tests. The load line displacement is not good for all the experiments. It's good for just a K at 15 MPa per Newton meters. We might think that the main difference is on the primary part of the load line displacement curve, and that part is only associated to the correct creep behavior representation for the material. But if we analyze the slope of the curves, those are very similar to the experimental ones. So we think that we might need additional creep tests at higher stresses in order to be able to cover also the range of stress intensity factors of 19 and 21. This is the uniaxial ductility sensitivity of the simulation. So we are, sorry, I forgot to tell. In order to obtain these results, we have used two values of uniaxial creep ductility. For the 2D simulation, 0.13, and for the 3D simulation, 0.24. We're going to discuss it now. We have applied both values to both simulations, 2D and 3D, and we have seen that the 3D model is significantly affected by the uniaxial creep ductility, so the time to failure is reduced by 1/10. Although the uniaxial creep ductility obtained of 0.24, it's expected to represent better what's happening at high stresses in uniaxial creep curves, while the low creep ductility that we have obtained for the 2D simulation, that might suggest that actually the specimen is in intermediate condition between plane stress and plane strain. So for this reason, that's too low for p91. C-star was calculated by the numerical simulations with two techniques. First, we have used the load line displacement and the crack propagation data from the numerical simulation. The formula is always the same. And also we have estimated it with the abacus C of t integral at different crack contours around the crack tip. And you can see also they are compared to the experimental data in black. So the transition time was estimated as per the AESTM standard, and also by analyzing the crack contour C of t at different crack contours. And it turned out to be equal to the experimental data, so almost 35 hours. And even if we cut out that part of the curves, we still have a region at very low crack strain rates, where the relationship between C-star and crack propagation rate is not unique. So this is something that might be investigated. Maybe also analyzing the damaged zone around the crack tip during the simulation. That's the closure. So we have performed an experimental test of CCG on p91 at 600 centigrade degree to estimate the C-star parameter experimentally. Then we have applied the ground wall script model and fitted to our experimental data and validated with numerical simulations. Then we have performed new 2D and 3D numerical simulations to predict crypt crack growth at different stress intensity factors. We have a good estimation of the crack propagation. The load line displacement was estimated good only at the case at K0 equal 15. And then we have calculated for this case the C-star parameter based on the results of the numerical simulation. And that's all. Thank you for your attention.